times, I still have not learned very many Portuguese words. So the talk will be in English. The slides are in English, my speech is in English, that's how it works. However, on the cab ride over today, I saw a horse. I knew the word for horse, a horse drawing a cart. I said, caballo. And the cab driver started speaking to me real quickly in Portuguese. I said, no falo português, caballo. So that took care of that. Anyway, so let's go ahead and get started for the talk that almost wasn't. A brief introduction to Git. So, as an overview, I'm going to go over, I guess this doesn't work over here, there we go, key concepts of Git, using Git by yourself as a way of tracking stuff, and also using Git with others, which is probably how most of us use it. So the most important things to know about Git are that, and how it distinguishes itself from other change control systems, is that it manages trees of files, not individual files. So it's keeping track of the changes you are making to a set of related files. You'll put this together in one repo, repository, short for repository. We call it repo. It also stores the entire history for a commit. So when you say, this is the version that I'm basing my work on, it knows not only that version, but all the previous versions that ever led up to it. And this is an advanced feature of Git and makes Git very powerful for doing things like branches and merges. It's serverless, and I say this to distinguish it from things like CVS and SVN, where in order to do any use with it, you have to have a server somewhere running, and your commands are talking to that server. In Git, most of your commands are acting on local files. Only occasionally do you then, when you want to share a commit, or you want to grab other people's work, do you then talk to some server. It's also intended as a source code manager. It's not very good at doing things that aren't related to source code. For example, there's no metadata. There's no information about each file as to whether it's mode 644 or mode 600, or what kinds of data might be in the file. It also is pretty bad at dealing with binaries. Binaries tend to simply bloat to the internal database that it uses. It's not good for storing that. That doesn't mean that you can't do these things with Git. It just means that Git isn't designed to do that. And so you're working against the design when you work that way. And particularly, Git is optimized for the common software development problem of two people working on the same code or code in the same area, where they go off and do independent work, and then the work is brought back together. We call this in the Git terminology branching and merging, making two different versions of something, then bringing those back together in an organized way. Git is very, very, very good at doing this, better probably than anything else out there. And so one way I like to say when people ask me, can I use Git for this or use Git for that? I say, are you branching and merging? Or are you just tracking history? Or are you just trying to move files around? If you're not branching and merging, don't use Git. It's the wrong tool for it. People try to use Git as a way to deploy code. People try to use Git as a way of tracking their entire home directory. But think about it, when would you branch and merge your home directory? It doesn't work like that. So if you're not branching and merging, please don't use Git. So let's talk about the moving parts. Inside the .git directory in your repo, you'll see an object repository. And this is at the heart of what Git is doing all the time for you, is managing these objects that are in there. Objects consist of the files that you're editing, the directories that contain those, and importantly, the commits. A commit is an object as well. So Git manages these things in the .git directory at the top level of your repository. The .git directory also contains things like operational files, configuration files, and so on. I won't have enough time today to go into the details of the configuration files, but needless to say, there's plenty of documentation on those. Also, you need a place to work. So you have a working directory. This is the current checkout of all your files, so you can edit them with your favorite text editor, and so on. Git also has a couple levels of command line tools. We'll see examples of those later in the presentation. We have two different versions. We have low-level command line interfaces, which in the Git terminology is called plumbing. Normally you don't invoke the plumbing. That's typically invoked if you're writing shell scripts that have to have a consistent way of interfacing with the Git repository. Normally you'll be invoking the porcelain, and that's most of what I'll be showing this afternoon. And that's the high-level code. That's the things that actually might change from release to release. So the developers of Git have said, don't build scripts on top of the porcelain, only build releases, or only build tools on top of the plumbing. Because the plumbing is guaranteed to move forward in a non-breaking way, whereas the porcelain might change if somebody has a better way of showing a file or doing something with it. On top of all that, which again I won't get to today, are various GUIs, various ways of looking at it in a graphical way. For example, to actually see branching and merging as lines on a graph. Very nice stuff. And then of course we've also probably familiar with various web user interfaces. For example, GitHub, a very popular website, has interfaces that talk directly to Git repositories to try to determine what branches, what merges, what commits have been made, who made all that stuff, and so on. So I keep talking about commit. Let's actually go into detail now of what I mean when I say commit. It's a unit of work. In other words, I want to make my product or project better, so I'm going to change a series of files, maybe just one file, but usually many files in relationship. And so a commit is capturing the state of that particular file tree. A commit usually came from something else. In other words, I'm changing something into something else. We call that the parent commit. So for every given commit, we'll almost always have a parent commit that says this was the state of the world before I made this change. Now it's important to keep that relationship in mind because it explains most of what Git is able to do well, which is keeping track of the parentage, the lineage of how we got these files into this place. That's what Git's really good at. Occasionally, when we bring work together, we have two or more commits. And that way we have a commit that has multiple parents. Again, Git is using this parentage information to determine how to merge files together when you do some work and then I also do some work. It has to know this history to be able to do that properly. Occasionally, well, initially in every single repo, you make a first commit. Now, obviously, you didn't change it from something else. It was just there. Maybe you commit an empty directory or something, but usually you commit the first state of the files as you need them. And we call that one a root commit. There's generally only one in every repo because everything else is built on this commit. So it's only going to be seen once. A commit also contains, there we go. A commit also contains some metadata. For example, who made the commit? A little message that says why the commit was made. This is what you tell Git when you're making the commit. I'm committing because I'm fixing this bug, or I'm updating this feature, or I made a typo in a file or something. It also has timestamps, so it knows precisely when that commit was made. This is helpful to sort out, was this a commit that was made yesterday, or was it made 3 weeks ago, or so on. And also very important, a commit contains a way of representing the tree of files that existed at the time that commit was made. So this is what a commit consists of. It's a unit of work, it has a parentage, it has metadata, and it has a list of the files, a tree of the files at the time of the commit. So what's a tree? I'm introducing here a new term, a SHA-1. A SHA-1 is a way of taking a bunch of data and turning it into a 40-character hex string. It's a checksum, or a hash, if you'll call it. So, in order to represent a tree in Git, Git will take the SHA-1, the checksum, of every file in a given directory. It then stores the data for those files indexed by their SHA-1s inside the object tree. And it does this in a very efficient way. So inside this object repository, if we know what the SHA-1 of something is, we can get the original data back. That's Git's first job. But then, how do we represent an entire tree of files? We take the SHA-1s of each of the files, and we just put it in a plain text file internally, and then we take the SHA-1 of that. So now we know for a given SHA-1 that represents a directory, we can go to the object database, pull out this plain text file, and then we have the SHA-1s of every file that was within that. So we have an efficient way in one 40-byte number to know the entire tree of files that existed, because we can do this recursively. As you're making a commit, Git goes down to every file, computes the SHA-1, goes down to every directory, computes a SHA-1 of a meta file representing everything in that directory, all the way right up to the top. And so now we have a single number that represents the entire state of how things work. So these are kept very efficiently in the object store. As Git is moving things into the object store, in order to have a way to go from the SHA-1 back to the original data, it's looking for files that are similar, areas of the file that are compressible, and so on. So as it's storing into the object store, it's actually compressing it at the same time. This means it's actually being stored underneath .git in a way that's more efficient than if it was simply files sitting in the file system. What's interesting about this is that if you have two identical files anywhere in your check-in, they will both map to the same SHA-1, because identical bits hash identically. So what Git does in this case is it just stores it once. It only needs to store it once because it already has that data under that SHA-1 in your system. So imagine a big project where you have the same boilerplate file in every directory. Git only has to store that just once because it already knows the same SHA-1 for all the files. Even at a higher level, if we take a set of identical files and put it in a directory, then the SHA-1 for that directory will also be the same. So you only have to store the same set of files in a tree once in the database. Again, very efficiently. This also means that Git can quickly determine when you rename a file or even rename an entire subtree within your project that it's simply been renamed. So it can store it efficiently and just say, oh, no, this is over here now. We already have it in the old place, and now we also have it in the new place. Again, only storing it once. So how do we make commits? We're going to use our favorite tools, text editors, whatever, to make changes to the working directory where your files are checked out. We then have to tell Git what we want to commit. The commands for Git all start with the word Git, and then a space, and then the subcommand. In this case, the subcommand is add. When Git is about to make a commit, or when you're about to tell Git to make a commit, it works off a thing called the index. The index is all the files that participate in the next commit. Typically, it'll be everything you just made changes on. But sometimes you make changes on a lot of things, but only a couple of them you want in this particular commit. Maybe you want to commit part of it to say, that's the change I made to fix this bug. And you want to commit part of it a little bit later to say, well, then I added this feature. But you want the commits to be separate in case somebody wants the fix but doesn't want the new feature. You can use git add with a subset of the files in your current directory and say, I only want those to go into this next commit. And then once you've done git add, you then use git commit. And a text editor will pop up asking you for the message that you want to have associated with that. At this point, git commit will update the head. The head, all in caps like that, is a special name. It's actually a SHA-1 that says what SHA-1 commit represents the same thing as what's in your work dir. In other words, this is the commit that maps to where my work is currently at. But before it updates the head, it says, wait a second, there already is a commit that represents the current work dir. That's head. So it saves the value of head, constructs the commit, and as it's constructing the commit, it puts the old value of head as the parent. This effectively makes a chain. If we do this over and over again, every commit will have as a parent commit the commit SHA-1 that represented the previous state. We make a little linked chain that way, and that's what Git is always tracking. If you're familiar with the words, that's a directed acyclical graph, but you don't have to know that. Now, for convenience, we also want to talk about the state of things as I'm working on this particular part of the project versus when I'm working on some other sort of interesting thing. So we give these head values names that we can remember, easy names that we can remember. We call that the branch name. For example, a typical branch name is master. So head actually doesn't point to a specific SHA-1. Head points at the branch name master. And master is what's moving forward as we make each commit. So it's one level of indirection there. So the branch is actually what's being moved forward. The branch name is being forward from one commit to the next commit and to the next commit. Now, in loose terminology, we would then also call that places where master has been the master branch. But don't be confused. The branch is really just the name master, and the commits that are along that trail don't have any knowledge that they were at some point part of master. There's nothing written in the commit that says I am on the master branch. The only thing that knows the word master is the thing that's currently holding the SHA-1 of the head of what you might call the branch. And that's important to understand because I know a lot of people get confused about trying to figure out what all the commits are in the master branch. Well, that doesn't make sense, really. It doesn't work that way. So the commit also gets a SHA-1. Now think about that for a second. If I create a commit, and a commit consists of all this information, including the tree of the files that existed at the time of the commit, then that SHA-1 is very important. Because it defines, there we go. The SHA-1 of the commit defines all the metadata of the commit. Who made the commit? When did it get made? And so on. The message in that. The tree of files. So in other words, it identifies specifically what your directory looked like when you made this commit. It also uniquely identifies the parentage, because the SHA-1 computed on the commit also includes any parent commits as part of the information. So the parentage gives us the previous commits. Thus you can look at it this way, that the SHA-1, if you know the SHA-1 of a commit in Git, you not only know what's currently in the tree, but you know every parent, and by deduction, you can determine every file of every tree ever committed that was in the parentage of this particular commit. And this is important because when we start sharing work, when I start sending work to you and you send work to me, we can use these unique SHA-1s to figure out exactly where we both diverged. Because if I send you a commit in all of its parent data, you'll be able to tell, looking at your repo, where we diverged, where the common ancestor is. And this is essential for being able to merge data. So we want to be able to talk about these commits. We can use the SHA-1 directly. Now a SHA-1 in Git is 40 characters of hex. It would be really annoying if I could only type exactly 40 characters of hex every time. Well, it turns out that even in a large repo, like say the size of the Linux kernel and all of its history for version 2. whatever right now, and 3. whatever since it rolled over. Even if we have a huge repo like that, we only need to specify the first 7 or 8 SHA hex characters to be unique. So if we see something that starts with A3F1, we can just type that in. Now, if it actually maps to more than one value in our current object repository, Git will come back and say, that's ambiguous. You need to type more. So then you just go back and do that again. Of course, this is great from the command line. If you're writing scripts, you should always use all 40 hex characters so that it guaranteed it wouldn't come back and say, by the way, that's not unique. Because with a script, how would it know when to do that? We also have names for some of the commits that are important. For example, head. Head is the name of the commit that represents our current work directory. In other words, it's sort of the object version of what's currently existing in the work files. Branch names are also another way to name a particular commit, like master or something else like that. We'll see how that comes in a few minutes. We can also give a particular commit a tag. For example, we might say that this particular commit represents version 1.5 of my software. And then when we push that data up to a repository, when someone pulls it down, they can name it version 1.5 and know that it means this particular release, this particular commit. As you're making changes, some of these might move around. Obviously, head's going to move around as you go through and make new commits. The branch names will probably move around as you make commits. So we can also access up to a limited period of about 30 days where all these were in a previous time. For example, we could say at yesterday in curly braces, and that would be the head that was true 24 hours ago. So this is handy, for example, if you want to see all the work you did between yesterday and today, you could actually diff from head at yesterday to head, and it would show exactly the work that changed. Or you could just number the versions. Head at 1, head at 2, head at 3 would be the previous 3 places where head was located. When you get into sharing work with others, you'll have upstream versions of some of the branches that you're sharing. In this case, head at upstream would give you the information about that. And any of these that we just named, that I just named, can also optionally be followed by tilde-n for the nth ancestor. For example, if I did master tilde 3, that would be the third parent, the great grandparent of the current commit on the master branch. If you leave the n off, it stands for 1. So head tilde would be the commit that was the parent of the current commit that you're working on. So when we create the repo, we create an initial branch called master. But the name master is not special. It just happens to be the name of the first branch created. I can get rid of master, replace it with anything else that I want. There are commands to do that. But here's master being my first branch. So suppose I've been doing some work and I've got some commits in master now. And now I want to work on something, a new feature, for example, or maybe a new bug fix. The most common way of doing that is to actually branch. Since branches are easy to make, just one command, and easy to bring back into the original workflow, branches happen quite frequently in Git. So here, for example, if I have master checked out, which is the initial default, and I say git checkout-b topic 1, this will cause a new branch to be made called topic 1, starting at where I'm currently checked out. So, topic 1 is set to the same SHA-1 as the previous branch, like master. The head is also now pointing at topic 1. What's the implication of that? That means that as I add new commits, they're now going to move topic 1 forward, instead of moving master forward. Master will still be there, and it will be the parent, and then eventually the grandparent, and then eventually the great-grandparent of the current checkout. But it's because we're moving topic 1 forward that makes the changes. So I could, for example, switch back to make more commits on master by using git checkout master. So that's the basic workflow. You make a new branch and you commit to it until you're satisfied. But we don't have to be completely satisfied before we can start working on another project. I'm often sort of easily distracted, so maybe I work on 2 or 3 different things at once. So we could, for example, say git checkout-b, similar to before, topic 2. This is another thing I'm working on, and I'll add one extra parameter there, master. That means go back to master and make topic 2 the same as master, not to what I currently have checked out. So now we've got a new branch starting again at master, but now it's called topic 2. So again, I would work, commit, and that's going to slowly move topic 2 forward by adding new commits to there. And I can switch back and forth at will. Git checkout topic 1 will change all the files in my work directory to be whatever the current head of topic 1 is. Git checkout topic 2 will change all the files to be whatever topic 2 is. And each of these topics are recording independent deltas on top of master. So if we do some work, let's say originally master was the commits A, B, and C. So C was the current master. And then we created topic 1, like I showed in the previous slide, and we did 3 more commits. We'll call them D, E, and F. So F has a great-grandparent of C. Another way to say that is topic 1's great-grandparent is master. If we do different work on topic 2, we're going to get, say, 3 different commits. So topic 2's lineage looks like A, B, and C, which they share in common, followed by G, H, and I, which are different changes being made to topic 2. Okay? So now it's time to bring those back in. Let's say I'm satisfied with the work I've done on topic 1, and I'm satisfied with the work I've done on topic 2, and it's time to bring those together. Bring back to master so that master can move forward. So we do it with this. We would say git checkout master, which will cause all the files in the current directory to look like they were at the commit C, if you recall from the previous page. We then say git merge topic 1. In order to perform a merge, git takes the current checkout and the named commit, in this case topic 1, and it looks for the common ancestor. Where did they diverge? Well, since C is a direct descendant, since G is a direct descendant of C, they didn't diverge at all. It's still at C. So this kind of a merge simply moves the master commit to be the same as topic 1. In the terminology, we call this a fast-forward merge. There's no work really to be done except to slide master right up alongside topic 1, both pointing at the same commit now. Now master looks just like topic 1. At that point, I no longer need topic 1. So I'll delete it. Git branch -d topic 1 removes it. It never existed. It's gone. I can't see it anymore. And that's good because that means you can create a branch to hold your work for a while until you're satisfied with that particular activity. Then you merge it back into master and get rid of it. No reason to hold that around. So this was a fast-forward merge. So if we looked at the pictures now, we'd see that master is A, B, C, D, E, F, the same thing that topic 1 had before. But topic 2 is still A, B, C, G, H, I. Now while I have this diagram up here, I'll show you now what would the common ancestor be for those 2 branches. It's C. C is the first commit that is in both of those branches. Git knows how to find those particular most recent common commits quickly. And that's important when we do real merges that actually have to do work. This one, not much work, just moving a pointer. Real merges take some time. So let's talk about what really merging looks like. So we want to bring topic 2 back into the mix. But topic 2 has gone a different direction than where master is now. There's 3 different commits on each of the branches. So in order to compute that, Git has to figure out the common ancestor. And it calculates, through its logic, that the most recent common ancestor between master and topic 2 is in fact C. Now why is that important to note? If you had a file in master, but didn't have that file in topic 2, and you tried to merge those, would it need to add the file or would it need to remove the file? How do we know whether it was added or removed? The only way to do that is to go back to C and go, oh, in C the file was there. Therefore, when I merge it, one side deleted it, the other side left it there. So obviously the delete is the better one of the 2 because it's more change. That's how the merge logic works. It needs to go back to the common ancestor to figure out what stayed the same and what changed. And it prefers change over the same. Okay? Now, this might cause some conflicts though. Because let's say in one file, you made a change that was one kind of change on one branch, and then in another file, you made a different kind of change to that same file. Now Git doesn't know what to do. It has to rely on you to fix it. So as a result of the git merge command, you may get a message that says these files have conflicts. And it will put messages about that out so you can actually sort that out. Okay? The new commit then is going to have both F and I as parents. So if we looked at the tree now, we're actually creating a brand new commit that's beyond both F and I that has both of them as parents. When we do a merge that's not a fast-forward merge, we'll have multiple parents in that particular merge. This also means that the history is no longer linear. We can't just say what is the parent of this commit, because some of the commits actually have multiple parents. So it makes it a little bit harder to use some of the tools. If we look at it on a graph, we'll see that DEF and GHI are actually parallel lines. There is a way though, especially if you're working by yourself, there's a way to make a linear history. In this case, we can take ABCDEF, that master branch, and ABCGHI, the topic 2 branch, and we can say, I want to take GH and I and play them on the end of DE and F. In other words, make it as if I did G on top of F, and H on top of G, and I on top of H. This is done with a Git Rebase. So I would check out topic 2, because I'm moving the commits around from topic 2, and I would say rebase master. In this command, Git will figure out where the common ancestor is, in this case C. So it knows that the commits G, H, and I are the ones we're trying to move. And it figures out the difference that G made on top of C, the delta, if you might consider it that, maybe like a patch. And it applies that patch on top of F. So whatever change G made from C now becomes, in this diagram, G prime. It's a G sort of, but it doesn't end up with the same file tree, it ends up with the same difference from its previous commit. Similarly, H prime and I prime are computed to be able to be a linear track. Now, because we're again applying changes, now in this case 3 times, we might have a merge conflict each time. Again, Git Rebase will stop and say, I'm stuck here, you need to figure out what I really mean when I apply this to that, and then you can say continue. So there is an interaction for that. So we might be getting conflicts at each one of those replaying of those deltas. So it's a little more complicated, but it's a really interesting feature because we now have a linear history, A, B, C, D, E, F, G prime, H prime, and I prime, that represents the 9 different commits that were in the original repo. Interesting project. Now, you then have to clean up when you're done. We have this all under topic 2. We really want it to be under master. So we check out master, we git merge topic 2, which will be a fast forward because it will just say, well, master is a parent of topic 2, so therefore I can just move master forward to do the merge. And then of course, we're done with topic 2. So this is pretty basic concepts to Git, but it's probably the most difficult thing to get about Git. How do merges work, how do rebases work, and why would you care? Both of them can have conflicts. A merge makes a bushy tree, a tree that has parallel lines in it. For some people, this is confusing. It's hard to use some of the tools when the trees have more than one parent for a given commit. So it's hard to peel out this sort of linear history. A rebase makes a linear tree, but it does it by getting rid of commits. If you and I are working on the same project, and you sent me the updates, the commits, that included G or H or I, well, I'll have G, H, and I in my repo. Okay, but then if you rebase G, H, and I on top of D, E, and F, G is gone. It's G prime now. G is not going to be there anymore. So when I take more commits from you, I might get duplicate commits now, because I'll have something that made the change that G made in 2 different places in the linear tree. And that's complicated, confusing. So rebase is nicer. It makes a linear history, but you need to take care if you have any shared commits. So for example, if you're working in a central repo and you've pushed some of your commits out, you don't dare ever rebase those. Those need to stay in place. So in terms of practical commands, using Git on yourself, You can create a repo at your top level directory. So let's say you have a series of files in a hierarchy and you want to now track them so you can rewind it or see what your work has been. Or maybe get other people involved. So we would take git init, which will take the current directory and add a .git directory underneath it. It'll also create the initial repo, it'll create the initial objects and the initial configuration. We then say git add -A dot, or git add and just list the files directly. The one with the A dot is recursively go down and add everything. That's the guaranteed way of getting everything. Or again, if you just have a few files, git add and a star or the names of the files, Git doesn't care. Now what the add did is, again, it moved it into the index, and that's Git's word for what will be committed when you next do commit. In this case, git commit is going to invoke a text editor, and you'll say, here's the initial state of the files that I'm interested in tracking. So you now have a single .git directory, and the current working tree, the current working directory is snapshotted as a root commit, a commit that has no parents. So this is the beginning of history for your particular repo. Now you want to do some work, so you edit some files, and you can use the Git Status command to tell you you've edited some files but you haven't added them to the index, or maybe you've added some files and they're changed now from what the index has. Git Status is a good command to know. Typing it over and over again is very handy. If I had time to do an actual demo, I would show this better, but just know that Git Status is a command I type pretty much every other line. So then when I've edited some files, I can add them all and do git commit again. Sometimes that's a bit overkill though. If you're just editing files that exist already, the git commit command can have a -A switch, and that says, go ahead and re-add the new state of all the files I've edited, but are already as part of the previous commit. In other words, add all the changes. It won't add new files though, so if you get used to doing this, and then you add a new file, Git won't track it. Git won't even know it exists, because you haven't done that first kind of add command to that. So you have to tell Git explicitly, yes, I want this to be part of my commits. So the initial git init made a master branch. So you're making commits on top of master. So let's look at some common commands you might want to use as well. And I know we're almost out of time here. Git diff, actually not doing too bad. Git diff is going to show you the difference between the index and the working tree. In other words, as you start editing files, the contents are going to be different than they were in the previous commit. Git diff without any arguments shows the differences of the work you're currently doing. So these are the things you should git add if you want them to be part of the next commit. Or git commit -A will also add all of these. If you give the diff command a parameter of head, Git is going to compare the working tree directly with the previous commit. And you may say, well, wait, isn't that the same thing? Well, maybe not, because if you've added some files already to the index, then they won't show up in git diff, but they will show up in git diff head, because it's a difference in the working tree back to the previous commit. So it's slightly different diff. And again, git commit -A will make that empty. And then just for the third leg of that, since we're talking about comparing three different things, we have git diff cached. And that's the difference between the previous commit, head, and the current index. That's going to show the differences that will be recorded if you just simply said git commit. So that's like the patch that you're creating with the git commit. Okay? There are many other useful commands. I'm just going to enumerate a few of them so you have a sense of what you can use. You could have git archive to take a commit, like head, and export it as a tar file or a gzip file. You can use git bisect, one of my favorite commands. Suppose you break something. You've been working on a project for a while, and some commit somewhere in the middle has broken something. You can tell bisect, this one is good here, and this one's bad here, but I don't know where I made the transition. Git bisect will automatically figure out halfway down one of the commits for you to try. and then you test that and see if that breaks it, whether it's good or bad. If it's good, you say, that one's good, and it will continue to keep bisecting between the good and bad ones that it knows about until it finds a specific commit that has made the change. Very handy if someone breaks code. Especially handy, I am part of the team of people that make sure that GNU Emacs compiles everywhere. And so every day I download GNU Emacs, and sometimes it breaks because nobody's tested it on OS 10. And that's what I'm doing, I'm compiling for OS 10. So I'll use Git Bisect to figure out what particular commit broke it in particular on OS 10. And then I get to tell the developers, hey, this commit broke it, something around here needs to be fixed. Or if I'm feeling particularly smart, I'll fix it myself. Not happening, okay. Cherry pick. Sometimes when I'm working with someone else, I like a particular commit that they made, but it's in the middle of a bunch of commits I don't want to use. I could rebase the whole set of commits on top of my file, but with cherry pick I can actually pick out a patch from a different chain and say, yes, that's a commit I like. So that it would apply it similar to what Rebase does and puts it together. Git move renames a file. So it's the same as just simply renaming the file, but then also telling Git that you've done the rename. Git doesn't actually record any specific renames. It actually does it by looking at the SHA-1s to tell what's been renamed. Git RM removes things. Git revert allows you to add a commit that undoes the result of a previous commit. And very handy when you're working with a team of people, Git blame. You can use Git blame to annotate each line of code with the name of the commit and the name of the person that added it. So you can say, oh, there's a bad line there. Ah, Jim did it. Ah, okay, go back to Jim and say, bad line, okay. Git log allows us to look at how things have changed. It walks through the heritage and picks the changes. We can print the patches as well. We can actually see how many lines were changed. Very handy to get a sense in a project of how things have changed. A lot of other things here. I don't quite have too much time, so I want to get to the good stuff coming up. Using Git with others. So you can use Git by yourself, and it's very effective for keeping track of files that you change. I'm working on a lot of projects for my clients, and I like to keep track of it so I can know how something broke, or that I can point to them and say, you told me to turn it this way this time. That was on June 4th. Now you're telling me to turn it back. I just want you to know you're telling me to do things differently. Okay. So these commits, as we've been making them, can be transmitted via many protocols. I could just hand you a USB key with my repo on it, and that's one way. Sneakernet, that's one way to get the commits. We can also use HTTP and HTTPS to pull down commits from a central repo. This is not the most efficient way of doing it though. There's a thing called Git protocol that can operate over TCP, but it's essentially unsecure. There's no authentication in it, there's no privacy in it, but if you're using it locally, this isn't bad. Most stuff these days is done with using Git over SSH. So if you're going to use a central repository, you'll probably have to exchange SSH keys with them to say, I want to be able to push and pull my commits to and from you. So typically, when you're working with others, you're going to be cloning a repo. What a clone does is it copies the objects from somebody else's repo into a brand new repo for you. And it'll typically have a syntax that looks like this: git clone, and something like user at host, and some path to the repo. In this case, user at host is in fact an SSH key, so you have to have the right SSH set up. But it makes a local thing called repo.git that also is checked out the remote head. The remote head is going to be what's checked out. So whatever the remote head is set to, that's what you get. In addition, it records the fact that it came from that repo by adding that as a remote named origin. Nothing special about the name origin, it just happens to be what git clone makes as the initial name. So typically what you're going to do to work with that upstream is you're going to work on your local master. Edit, edit, commit, commit, edit, edit, commit, commit. And then when it's time to share your work, you've made the change that you want to make, you want to refresh from upstream. There's a couple ways to do that. We could do it by merging. In other words, we have a bunch of commits that we've made since the last time we refreshed, and and they've probably made a bunch of commits in the meanwhile. By saying git pull origin master, you're going to say, go over to the origin repo, whatever it happens to be defined as, grab the master branch from there, and do a merge with my master. So it will make a bushy tree. It'll make parallel tracks and try to pull it together, and in fact might cause conflicts, which you'll have to sort out. Another way to do that is by a rebase. Git pull -- rebase origin master causes it to make your work sit on top of the remote master commits. And that's handy because it creates a linear history again. But again, you cannot do this if you've already pushed some of those commits to someone else. So only if you know the things you have locally are really, truly local and have never been gone somewhere else. Once you've done that, you should also have permission then, if you're working with other people, to push origin master, which will efficiently calculate all the commits that you have that they don't, and send all those up in a nice compact bundle. So pull is grabbing down only the commits that have changed and the tree parts that are parts of those, and push is only passing up the parts that are on the other side. This is all managed by all the SHA-1 indexing. So it simply looks at all the commits and says, I have these SHA-1s, do you have those? You say, okay, I've got almost all of those, but I'm missing these. And then they go back and forth to decide which SHA-1 files also have to be transmitted. You may want to just see what changed before you do that. You can do git fetch origin, and that doesn't actually pull it into your database or pull it into your local repo, but rather it pulls it into tracking branches that are set up by Git. And the name of the tracking branch in this case is origin/master. So now you can do a diff between your current master and origin master before merging it in. It's really nice to be able to see if somebody else's work is going to mess up your work. So you can do sort of a trial balance that way. That's about all the time I have. Let me put up a couple of slides for further information. Git in the Wikipedia amazingly has great information. The Git homepage is gitscm.com. You can also go to the Git wiki at git.wiki.kernel.org. Great information there, including lots of presentations like the ones I've made are listed from there. The Pro Git book, totally free as in you can just download it. You can buy a hard copy of it, but you can also just download it and look at it. It's an incredibly well done book, lots of great graphics and stuff. And you can also get on the Git development mailing list. Beginner questions are tolerated there, nobody has a problem with that. And there are helpful people there. And you can also submit bugs and patches and ideas there as well. And there's the incredibly helpful and wonderful Git IRC channel. I'm on there a lot of times answering questions for people, but a lot of the key developers are also on there to help you out. And that's all I have to present. I think I have a couple minutes for questions. Yes? Yes. If anybody wants to ask a question, they may. And the crowd is wonderfully silent. Okay, thank you for your time.